My name is Dr. Yuen Tsang. I actually from a Department of Applied Physics in Hong Kong Polytechnic University. Today I will talk about some of the recent development that we have done regarding this Group 10 TMD 2D layer material used for laser photonics application. Basically, this material we use for two main applications. One is ultra fast laser pulse generation. As you can see from this picture, why we interested in ultra fast pulse, because long pulse, generally speaking, is about nanosecond pulse, which is can be achieved by using Qswitch laser. They have a relatively long pulse. Then we'll have more time for the heat to transfer to other area and damage the ceramic material. This is called heat affected zone. And if we can reduce the pulse duration, then in like picosecond, femtosecond, which we call them ultra fast laser system, then because the switch on time, the laser pulse is ultra short, so you don't have enough time to transfer to other affecting area. So that's why when we're using this ultra fast laser for cutting and laser processing, we can actually make a very smooth edge, as you can see from there. For example, those high-end electronic devices, iPad, iPhone, sort of like a screen. That smoothness will allow a stronger bending force the screen can withstand, for example. And of course, no need to say if we can have a smaller beam and also ultra fast beam, less affected zone, then we can actually produce a very fine structure like this micron structure picture we can see from the figure. No need to say in the future that ultra fast could also be used for the next generation optical communication system. And eye surgery now are using ultra fast femtosecond laser so that they can have a very little damage to the surrounding tissue. Precise cutting, precise manufacturing, they all need this ultra fast laser. So that's a tremendous application. So in the past, for pulse laser, for the pulse laser generation, they usually employ some dope crystal. They are rare earth based. Some of them are rare earth based. The absorption spectrum, emission spectrum, actually limited by the dope material itself. So more popular commercial available device, for example, like CSAM based, more commercial available. They are need expensive technique called MOCVD gold technique. You can make a gas vapor deposition layer by layer. So these are expensive technique and also have very low operation wavelength band. Okay. In fact, the scientists are searching new material that could replace this traditional commercial available material. So in the past, they have developed various material, including topological insulator, monochrome, carbon-based material, and within the 2D family, some of them have been tried before, like MOS2, WS2, but they have experienced different band gap. In the past, people interested in graphene, a carbon-based material, mainly because this is the first material being used as a 2D layer material for laser monochrome application. It is attractive because it's a carbon-based material, and this zero bandgap material will have a very broad absorption per layer. However, they also have some drawback because the graphene material have no band gap. So the light interaction is very weak. For example, for one layer of a graphene material, they only have a very weak absorption, around 2.3% per layer. So the modulating depth will not be very high. So that means not favorable to nonlinear application. Then scientists extend their interest into other two-dimensional material like TMD based material. So this material will form different material with a tunable band gap, because by changing, in principle, by changing the M and X, the chemical formula atoms between these two, we can actually tune the or have a different band gap structure. Now here is some figure we see. So graphene is a zero band gap material. You know, if you try very hard, you can open a bit, and black phosphide is a bit lower. So in fact, this MOS2, WS2 base, they are quite big. The band gap is quite huge. They are mainly in the visible range, respond to visible range. So now, what interesting about this group 10 material, because you can see that band gap can be very wide in a small band gap region. So that means you can use it for long wavelength laser, for example, infrared, this kind of wavelength. And they have some attractive feature, like some of them are metallic, so feature semi-metal. So you can also use it for other application like photo detector and things like that. So this is our pioneer work by using this PTSE2 material as a saturable absorber, which published in the Photonics research. We actually use this material inside our ND vanillate crystal. This is the crystal laser, so that's why we can have the pulse energy a little bit high. So here is our first demonstration, how we can actually confirm that this is a mode locking operation, because the pulse duration is actually agree well with the round trip KV time. Yeah. So this is the first demonstration. The material we use is a polycrystalline structure. We deposit our PTSE2 nanofilm within the substrate. Then the overall thickness is about 24 nanometer. It's a kind of nanofilm. So this is the characterization. The figure 2A, B, C is the characterization to confirm that this is really the 2D material we produce, polycrystalline, a few layer 2D crystalline structure we produce. So then we move and extend our interest to another 2D material, 2D group 10 material, that's a PD base material. So now currently for the group 10 material, generally speaking, is a PT base or PD base. And of course, in this, you can use a Sapphire or SE or other TE even. So in fact, this is another first demonstration regarding this PD base material used for saturable absorber application. So here is the material we produce here. They are sort of like in the nanofilm structure. And then you can have a look the overall dimension under the TEM, as you can see from here. So from these EDS, you confirm that this is a PD and S material produced, and the carbon is actually due to the holder of the observation, for the observation. So here we show you the crystalline. So again, they are polycrystalline structure. And we also have done some quantification of the size, every size that we produce. So basically, we're using some ultrasound technique to make it thinner and smaller, and then using some transfill to select the thin layer structure. So as you can see from there, that the FH fixed size is about 200, 2 to 300, and so it's pretty small. Yeah, it's kind of a nanomaterial. Then we add the PDS2 material on the side surface of a D-shaped fiber. That's one way we allow the laser in the fiber core to interact with the side surface. Okay, we can also put them in between the junction of two fiber to make sure that you can have a direct interaction between light and the 2D material inside. So this is a laser ring cavity. We also tune the polarization direction by changing the polarization controller. For production of Moloch laser, it is about the loss and gain balance. Yeah, if you can make this happen with the right loss and gain balance, then the Moloching pulse can be generated within the cavity. So here's a series of characterization of the laser power we produce. So the first demonstration from this work is a Qswitch operation. Okay, it's not a Moloching, it's a Qswitch operation. So the pulse width is a bit big. It's a 4.5 micron second. So one of the key features of this Qswitch operation is that the repetition rate and the pulse duration is actually changed over the pumping power. If you scale up the pumping power, because they actually have a more energy per pulse, right? So the pulse energy will increase. Yeah, the output power will increase, and as well as the output energy. It doesn't show here, but the repetition rate will change. So you're getting higher, as you can see from figure B. At the same time, the pulse duration reduces. We have a shorter pulse, and at the same time, the peak power also increase. Now here's you see the pulse is quite stable, as you can see from here. Peak to peak fluctuation is not a lot. So the wavelength produced about 1.5 micron. So we also try to use some nonlinear setting to test out the modulation depth. The modulation depth we got is about 1.4, 1.7. Yeah, between 1.7 to 1. A is the maximum, B is the minimum modulation depth condition. The modulation depth is actually depending on the polarization state of the input light. So here are some of the characterization. So one thing I would mention that in fact the laser performance is pretty good, and if you make them into a Moloch operation, okay. For the Moloch operation, that we clearly see the pulse to pulse duration in between is around 82.4 nanosecond. That was agree well with the round trip cavity time, and the pulse duration, yeah, is in the hundreds of femtosecond region, as you can see from this is the detected by the autocorrelator. And another concern is this is a very typical, the output against input. You see the increasing when increasing the input. So another thing we are quite interested to know that was about the stability, overall stability. The overall stability is actually quite good. As you can see, the wavelength spectrum, in fact, it doesn't change too much over time. So as a conclusion, that we actually demonstrate both Qswitch operation and Moloching operation by using the PD-based material as a central absorber as the first time. And then later on, we also use this group 10 material to make a photo detector. So this is the first demonstration that, and also a comprehensive study regarding the performance of photo electric effect by using this material. So we actually deposit the PDSE2 material on top of gallium arsenide, N-type gallium arsenide material, and form a heterojunction structure. Okay, so here's some characterization. After deposition, the color changes. You can see from there, from figure B. And our work is actually highlighted by the advanced functional material. It's a cover page article. So as you can see from there, that was done by metal sputtering technique. We're actually using several techniques to make this absorber, but for this particular one, that we deposit a polycrystalline structure. As you can see, some of them are actually vertical standing. Okay, so this vertical standing might have some effect on the absorption, spectrum. So that's why we characterize our photo detector with respect to the spectrum response, and we found that this material is capable in having a very broad absorption spectrum, very broad range, from ultraviolet to up to 1.2 micron. And the response is good as well, as you can see from the figure C and D. So there's a heterojunction form in between. So that's why when there was response with light, the electron hole pair will not be recombined so easily. That can further enhance the performance. So another piece of work we done is we demonstrate this PD based material for the first time with the silicon detector. Okay, silicon detector is just some of the quite traditional material. Yeah, so they have a very limited response bandwidth, but by recombining with the PD SE2 material, we also form a heterojunction, as you can see from figure D. And for this material, we actually make a metallic structure first. We deposit in some metallic layer on the surface, and then with some post treatment that we adding the SE material on the surface through a post annealing technique. So we can quite precisely, for this technique, we can precisely tune the thickness of our material. As you can see from there, the thickness is between 1.2 nanometer to up to 20 nanometer. So here is some of the thickness characterization you show here. And at the end, we demonstrate quite a good performance photo detector. Some of detail can be seen from the publication there. But this slide show here, it allows us to further enhance the property by adding some BP quantum dot. As we know, the PP back force by quantum dot have some absorption, have quite good absorption in the long wavelength. Okay, so so by adding this PP quantum dot on the surface, we can actually enhance the absorption in the long wavelength, as you can see from figure D, 6D. So 6D, the blue color on top, is a photocurrent response. You can see clearly due to the enhanced absorption of the light. So the photocurrent response is actually enhancing. Okay, they put it in a log scale. So that's why you can see more obvious change in this long wavelength. The long wavelength in between 1.2 micron up to 2.1 micron. So, and of course, in the visible range, they also have some enhancement, as you can see from the lower part of figure 6D. So surprisingly, this material, of course, the performance are not uniform, okay? But you can still see that this can have a very broad response range from 300, up to 2.1 micron. So, and the time response is also good. The time response from the figure E, you can actually see that the BP, after adding the BP quantum dot, the time response, the current is actually enhancing, without degrading the response time as well. And in figure F, this is a comparison between different sort of combination in between PDSC2 to silica and also BP dot on the surface at different wavelength, okay, in 2.1 and also 3.83 micron, okay. So we have another light source operating at 3 micron, so that's why you can manage to test the performance at 3 micron. So another work is also published in Advanced Functional Material. So sorry, there's some mix up between this. Yeah. So another piece of work we have done is combining the material with perovskite. So as you can see from this image here. So that was another collaboration that work we have done with other professors in China, Professor Law. So in this work, we actually try to combine the PD material with perovskite. And so perovskite is a very popular material for solar cell application, right? So again, we also using a similar technique. First deposit the metallic layer on the surface, and then we're going to add this SE material or S material. In this case, is SE material, right? During the post-annealing process. So the thickness is about 22.3 nanometer. For this work, due to the combination of these two material, we experience slightly different spectrum response. But generally speaking, this is more uniform. So it's range from UV up to near infrared. Okay. Now, for this work, we have done some slightly different thing compared to the previous photo detector. So in this work, we found that the photo detector is actually polarization sensitive. So what we're trying to do is we illuminate our photo detector by using a light source and go through a polarizer. So that means the light is actually polarized. And this, because this is unpolarized light source, after polarization, you can tune the direction, the polarization direction, okay? So then we can actually evaluate, so what is the response of our 2D material-based photo detector with respect to different polarization direction. So here is our result, as you can see from the figure H. Yeah. So what's going on is we tune from 0 degree, 360 degree, one round term. Yeah, you found that the photocurrent is actually changing with the polarization direction. Okay, so obviously you see that in this direction is the maximum, and 90 degree this direction is the minimum. So you confirm that the polarization sensitivity of our material. And more than that, yeah, we actually use array. We use this material and make a array. The array will allow us to, so the array is about 10 times 11, okay? So the array allow us to sense the image change. So we're using a metal plate, put it on the surface, then we can actually see the sensitivity of a different pixel, okay? By changing a different pattern, we can actually put the English word polyu as a short form of our university's name under the illumination of 808 nanometer laser source. So this is in the infrared region here. So to confirm that the potential of this material being used as a imaging sensor as well, not only a single photo detector, it's also an array with imaging sensor. So as a conclusion, with this PDSC2 material, in combined with the other Kawasaki material, then we can experience a very broad response from infrared up to 1.55 micron. And further photo response characterization reveal that it present a device execute very good performance in terms of high on-off ratio and also a large responsivity and specificity and also a good polarization sensitivity with fast response time. So the imaging sensing is successfully demonstrated and also confirmed the potential of using this PD-based material as a photo detector and imaging sensor. So the work relating to this presentation are published in this paper. So if you have an interest, you can have a look at them in details. And the work is actually supplied partly, some of them are partly or fully supported by the Research Grant Council of Hong Kong and with this grant code. So thank you very much for your listening. There's a time for Q&A if you have any questions.